Hey guys, this is Carl, and this is week 11, problem number 5. And just go ahead, I'm just going over this pretty slowly just to make sure that everybody understands, because as you know, we're getting more complex as the weeks have come along. So just getting started with this problem. A study of external disk drives finds the data in the company table. The least square line is price equals 19.29 plus 0.121 times capacity in gigabytes, with standard error of 10.82 and standard error of intercept 0.29, where the values are rounded and the number of decimal places shown. The assumptions and conditions for regressions are met. Use this information to complete parts A through C. So this is the data that we have. You kind of see the scrolling of capacity in terms of memory and the respective prices. X bar and your standard deviations, if you remember from a while ago. It's pretty easy in Excel. All you do in terms for your X bar, which is essentially the mean, you just type your average. You can just close the parentheses. For example, one matches this exactly with some rounding. The same thing for standard deviation, just to kind of review for everyone. I'm just going to use the older version right here. Same principle. So we should get 1498.72, give or take. And as you can see right there. So that's just an review of getting how did the question arrive at these values. So part A, disk drives keep growing in capacity. Some tech experts now talk about a petabyte, which is 1,000 gigabytes. So what does this model mean for 1.2 petabytes? Well, actually, it's 1.2 million gigabytes. That's my correction. So 1.2 petabytes equals 1.2 million gigabytes. So that is a key thing, just in terms of just the verbiage, just converting it in a sense. So how do we do this? Well, essentially, we are just inputting this conversion into our equation up here, 19.29 times 0.121. Why do we need to convert? Well, they give us 1.2 petabytes, but if you see, just like in algebra, we have to convert because our equation is in gigabytes, and we have to make sure that if we don't account for that, then we can have serious issues with, losing a decimal place. And in this case, a decimal place is very important because we're talking about memory size and cost for that matter. So as you can see here with the conversion, all it is in the equation formula, in the formula right here, is 19.29 plus the product of 0.121, as you see here, times the capacity. And just going to make sure and be careful about your zero. So this is 1.2 million gigabytes. And as you can see, as we're finished, the predicted price based on this is $145,000. So you can tell just by that this is more than likely not realistic for the average consumer. But your company's defense department, anything like that, this is probably more than adequate. So question B, find a 95% interval for the price of 1.2 petabyte drive. So we have everything that we need in this case. Now, the prediction interval, where YV is the predicted value. The predicted value is what we just saw right here, 145,000. XV is the value of the explanatory variable. What's the explanatory variable that we're looking at? Actually, it's our investigative option. We're looking at 1.2 petabytes or 1.2 million gigabytes. Tn minus 2 is the critical value of the t distribution at the specified confidence level with n minus 2 degrees of freedom. What does that mean? Just going down here, I think the best way in this kind of Excel format is to explain it bit by bit. So going down to here, t minus n minus 2, see, the t inverse function is how you really in Excel, how you find your t value. So we have 0.05. Where'd that come from? Well, actually, if you remember, it's 95% confidence. So what is alpha? In this case is 1 minus 0.95. So this is how we get that. Now the 5 is our n minus 2, which means that our n is 7. So where does 7 come from? It's really quite simple. 7 is up here. It doesn't look like it. It's not really intuitive. But if you see here, 1, 2, 3, 4, 5, 6, 7, we actually have 7 pieces in our data set. So if you scroll down, you can see. So that's why we got this value right here. And then standard error squared is the square root of the standard error of V1, and S squared E is the variance of the residuals. So as you can see, we've done that. Now if you scroll up to the top, they give the residual 10.82. Now see that SE, but in the actual equation for the predicted value, it's S squared E. So we have to keep that in mind. So as you can see here, we've squared that value right here. And then similarly, we've made sure that this square is divided by 7, which is our N. And then here, if you notice, it's actually squared. So it's 0.0029 squared. So it's a couple of things to keep track and make sure you be diligent about that piece, especially with the equation like this that gets pretty complicated. So it's YV plus or minus the Tn minus 2 times the square root of your standard error squared times the XV minus X bar squared plus the S, the residual squared divided by N plus the residual squared. So it's a little bit complex in this format, but that's why I broke it out by each category this way, so that you can kind of visually see how the formulas are there. So as I've explained, N is 7 in this case, so that's why we're divided by 7 for this. And we're squaring this because as the equation dictates, we need to square it. X bar, we find out earlier, it's the mean. Tn minus 2, remember N minus 2, so 7 minus 2 equals 5. And that's where we get that. And then just to make it easier, I went ahead and did XV minus X bar squared in a separate piece because it's so large. Just to kind of break it down, and sometimes in Excel you will have to break stuff down like this where there's these incredibly complex algebraic and regression equations that really by piece just to ensure your accuracy. So in looking at this, your confidence interval, your predicted interval, is actually between 154,000 and 136,000. Now give or take, now remember at the very beginning it asks to round, so give or take, if you round these to the digits, like the third, the thousandths place, that you'll get around kind of what the actual example online would tell you. So just to give you a good sense, these are just raw numbers, not rounded. I just wanted to show you for equation purposes without kind of cutting them off. And then part C, are these predictions likely to be useful? Well, using a regression model to predict a value for y for an x value that is outside the range of the x values in the data should be viewed with skepticism, and such a prediction is called an extrapolation. Extrapolations are dangerous because they require the additional and questionable assumption that nothing about the relationship between the x and y changes, even at the extreme values. So what does that mean? But kind of in a general format, is that if you have your data that only goes between 75 and 4,000 gigabytes, and you're actually trying to predict with a regression equation something as high as 1.2 million, you really have to view it with a little bit of apprehension because your accuracy, your rate of error is going to increase exponentially in this case because you just don't know. You just don't have the data points to reasonably assume that this trend would carry forward that far out, given this trend. So it's really kind of what it boils down to. So, but we just hope that this helps, but just let us know if you have any questions along the way. Thanks so much. Bye.